Yeah.
They emptied the pool halfway out. You know, I wonder what is it still going on?
I don't think so. But the water's going.
Look over here where Sue's asking out.
Yeah. I'm surprised we didn't have broken glass. Took about a foot of water, more than a foot of water out of the pool.
This is perhaps more relevant, I think. You would definitely have been alive for this, right? This is, I think, 2011. It probably said on there, I didn't quite catch it. The Mineral Springs earthquake, Virginia. I remember sitting in my office, being swayed backwards and forwards. You could tell it's not a truck hitting the building because the frequency is much lower than, a sudden impact for a truck, but the same basic idea. Yeah, okay. Much more gentle, but you can basically see what went on. I don't want that. Oh, yeah, another. And we looked at a derivative of this before. And it kind of is a precursor for what we'll talk about today. So last week, for week 3, the questions were related to fluid pressures on structures. So we know that fluid pressure varies at a point, and by integrating that on the face of a structure, you can get a magnitude of a force, and then you could look at stability of that, which is involved in whether the structure fails, whether the gate opens, whether the plug is buoyant and rises in the water. But all of the things we've looked at so far have really been static. And so we've derived the expressions for accelerating fluids, but we haven't actually looked at accelerating fluids in detail. So that's what we'll deal with today. We've made the point before, I think, that it's almost oxymoronic that we're talking about accelerating fluids when we're talking about static fluids, because something can't be accelerating if it's static. But the static really refers to the fact that there's no circulation within the fluid. The fluid is in your beaker as you're running across the room, and as a result of that acceleration that gets applied, there's a change in the level of the water. And this is just a leaky double glazed window in a bus that's going down the road. You see these seshes, these waves that get transmitted by sudden accelerations and decelerations, but overall with a long-term smooth acceleration, the angle of the fluid, the free surface, changes if you're accelerating forwards, and in the opposite direction as you decelerate. Almost like a bulldozer pushing a pile of soil in front of it, but it's a different process that's involved in this. And so we talked a little bit about this before. We made the point that when you look at the tank cars that you see that pull oil across the country, the Bakken oil, they're not just flat on the top, but they have an inclination at both ends and a depressed filling manhole in the middle. And that is so that when these things slow decelerate, it doesn't pile up at the end and pop the hatch and have a spill. And I presume that's exactly the design reason for that. And this is really the mechanism that's going on. So today we'll spend some time talking about accelerating fluids in static fluids. Other applications of this, this isn't really an application. Actually, it's a cool video, so let's watch it. So-called Helmholtz waves. It's actually due to viscosity.
Towards the horizontal. And frequent checks are made.
And the idea is if you can have a dense fluid that underlies a less dense fluid, as you'd expect to get, if you then cause a disturbance that makes the upper fluid shear past it, which is what's happening here, then you get these waves that you'll see on the right-hand side of your screen, which are really, they'll pop up, which are really cool. And it's not really anything to do with accelerating fluids, it's moving fluids, but it's viscosity. The viscosity of the drag on that bottom orange wave is what's moving it. So it's not really related to what we're talking today about accelerations, so, but a cool effect. And you see it actually in the atmosphere, in clouds as well. So one of the other things that we'll talk about is accelerating fluids, but in the context of radially accelerating. And so the mechanism by which a centrifugal pump works is it has some blades that go around, they take some fluid and they push it out to the exterior, and the exterior goes up into this vertical pipe, which means that since it's moving it, then it sucks in more fluid along this longitudinal pipe that's supplying it. And so in addition to linear accelerations, which we'll spend our time talking about here, angular accelerations that result are also we can deal with, and we'll deal with just briefly today, talking about that. Yeah, and that's it for now. That's it for the intro. And so really what we're returning back to is this idea of the bus. Might not seem like a completely practical idea. Whoops, this was one. But how do we figure out exactly what this elevation is of this? I mean, the implications would be in calculating, for instance, what the pressures are at the back of this pulse that might be applied on the back of the tanker cars. If you have tankers, which most planes have their fuel spread within the wings, but tanker planes have fuel in a tank inside them. So when you take off and land, what are the implications of what the fluid will do within that tank as you do that? You probably don't want to spill it, is my guess. So that's kind of what we'll talk about today. And so where we are is here. We're in the fourth week, as you realize. And so what we'll spend our time talking a little bit about today is fluids in these two modes. The first mode we've already dealt with, right? The first mode is basically this, the equation above here, which we derived maybe in 2.1. And we realized that the important special cases of this are when accelerations are 0, we get these two expressions, which we dealt with. This is basically the expression which we've used in weeks 2 and 3 to define pressures at a point, manometry, and fluid pressures acting on structures. But always our assumptions were that these accelerations were equal to 0. And so now what we'd like to do today is relax that constraint and use that to be able to say something about what we expect the behavior to be if we do that. And so what we'll do is we'll look at two things. We'll look at linear accelerations and we'll identify two questions. First is the orientation of the free surface. And the second is, how do fluid pressures change? In basically our coordinate system. How do they change in x and y? And how do they also change in the z direction? So those are the two questions we want to address. And so we won't use anything new from what we've had. You remember that we've had this expression before. You'll remember that in this expression, the two parts of this left-hand part is equal to forces. This right-hand part is equal to mass times acceleration. These are vectors because they can be in x, y, and z, and that's why we have three different equations. And we've written them out in longhand, and we've always assumed that these accelerations basically go to 0. And if we do that, we end up with the two red underlined expressions we have here. But we're going to relax that requirement because what we'd like to do is we'd like to know exactly what happens to why this phenomenon occurs that the inclination of the fluids changes as you accelerate. It's probably important to make this distinction that we're talking about accelerations. So if I was walking across this room with water in a beaker, then if I was moving at constant velocity, it would be flat. When I accelerate to get up from 0 to some velocity, it would be oriented like this. If I was going to the right side, I guess, yeah, the right side for you as well, right? But as I changed from an acceleration which was finite to one which wasn't, as I have a constant velocity, then it would flatten out like this. So it's always accelerations that we're talking about. So in the bus, when it goes up, it's accelerating forwards. When it goes flat, it's a constant velocity. And when it's decelerating, it's in the opposite direction. And so it may seem like a trivial point, but what we can use is our expressions that we have already to be able to do that. The three expressions that we have are these from this first page, right? We've written them in this compact form before. We realize that this is equal to force is equal to mass times acceleration. And actually, the units of these you can check, right? Pressure divided by length has to have units of newtons per meter squared meters, which are units of newtons per volume, right? So these are actually in force per unit volume. So if you divided this through by volume, and if you divided this through by volume, then not surprisingly, this is a density, by definition, mass per unit volume, multiplied by an acceleration in each one of these directions. And so when we look at rotational accelerations, exactly the same relationships, similar relationships will result, and we don't need to derive them, we can just do it by heuristics, by basically invoking this idea that what we'll use is, instead of force equals mass times acceleration, we'll use force is equal to mass times angular acceleration, which we'll use later. So you'll see that. But the point is, there's a direct relationship between these expressions that we have here and the ones we'll have in rotational equilibrium. So we made the point that we'd like to be able to represent this particular case. And so what happens when you accelerate a fluid? What we can do is we can assume that we have a container, a static fluid. That container is being accelerated with the fluid in it. In the earthquakes, it was being accelerated one way and then back, so it's not such a good analog for us because it's a dynamic state. It's not a steady state that we reach. But you get the idea. If the period of the earthquake is long enough, then you do reach a steady behavior for a while before it kicks back the other way. And we're going to assume that in our coordinate system, which is x, y, z, that we'll have accelerations in only two of those. So we'll accelerate in the y direction horizontally and acceleration in the z direction vertically. So a positive y and z acceleration is something that goes like this, right? This is the positive y direction in the right-hand rule. This is positive z upwards. And so this is positive ay, this is positive az, and a combination of them is this inclined vector, which is the vector sum of those two vectors. We're going to assume that the acceleration in the x direction is 0, just because we're not looking at that plane. We're only looking at a two-dimensional system. And so what we can do is we can use these relationships which we derive already, to be able to say something about how the free surface develops. And the easiest way for us to do that, I'm going to remove this in a minute by just coming back. Indulge me for a moment. So we can write that the change in pressure as you go from one place to another in the x direction, so this could be a change in pressure as you go in the x direction, a change in pressure in the y direction, and a change in the z direction. Actually, don't write that down. It's not quite true. Is that this is not 3 dp, because each of these are due to moving in a direction which is orthogonal to the other direction. So we go first in the x direction, then in the y direction, and then in the z direction, and you get each of these. So what we could do is, if we can write it in this form, that these are the components in each of these three coordinate directions, then if you believe that that's the case, whoops, did I want to do that? Delete. Does it? Yeah. So what we could do is we could just multiply this relationship here by 1, which is dx dx, this one by 1, which is dy dy, and this one by 1, which is dz dz. Right? So we've done nothing other than that. So now, if we've done that, we have expressions for how pressures change in the x direction, which is 0. We have an expression for how pressures change in the y direction, which is equal to negative density and the acceleration in the y direction. And we have an expression which is for changes in pressure in the z direction, which are equal to minus density times the sum of two accelerations. Gravity, which always acts, which is a positive number. Even though it acts downwards, we always assume that it's positive. That's what this negative sign here comes from. And an acceleration that we're going to apply in the z direction, which is going upwards. And so what this gives us is a new relationship which tells us how pressure is going to change as a function of these accelerations that we apply to it. And so now, if we look at the conditions that would actually exist on this free surface, so this free surface here, whoops, I didn't mean to do it that thick. By definition, the pressure on here is atmospheric. It's atmospheric here. It's atmospheric here. And so, I'm going to go back to a smaller one. And so, as we change across here, by definition, whoops, dP has to be equal to 0 as we go along this surface. So the pressure along here has to be 0. And so if we make this magnitude here 0, then we only have two remaining expressions that exist here, which are this and this. And if we rearrange those, and we go through the juggling that we do, we end up being able to pull out, this is 0, right? We can pull out this term here, dy, and we can pull out this term here, dz, and as a function of the physical properties of our system. The density of the fluid and the accelerations that we're applying it ourselves, ay and az, but also gravity which acts. And so this ends up being the relationship that defines that behavior. So physically, what that means is that if you look at the reference frame that we have, so this is maybe the bus, this is the y direction, this is the z direction. If we know that on that bus, the inclination of the fluid in that looks something like this, then this is dz, this is dy, exactly what this is, and it's a function of these components, right? And so if ay were 0, then it would be flat. If we're not accelerating horizontally, it would be flat. If az were 0, which it is in the system we're looking at, right? A bus going down the road, it's on a horizontal road, it's not accelerating in the vertical direction unless it goes up a hill or down a hill, then this would be 0. And so if you look at the case of the bus that we had, it was probably of the order of 1 to 2, something like that. It wasn't very, or 1 to 4, if you like. And you can use that directly to figure out exactly what the change would be. This would be 1, this would be 2, just from the equivalence of these. We know the acceleration vertically is 0. And so we know that the acceleration in the y direction, this has to be 9.81 squared, right? And therefore this has to be 4.9 something, right? If we wanted to match this. So It's quite useful. If it's a factor of 1 in 4, then it means it's going at a quarter of the acceleration due to gravity, but it allows us to be able to say something about, we could use it as an accelerometer, I guess, if you wanted to. So that's one option. So that's one option in this. In our particular case, the acceleration in z was 0, but we could also use this. So we know that if the acceleration horizontally was 0, but we're accelerating vertically, then it would predict that the surface was flat. But then the question we could ask ourselves is, what is the pressure distribution below that surface? We know that in a static fluid, the fluid pressure changes with the gradient, with the depth below multiplied by the unit weight, right? That's the pressure at any depth. So we know that we can get pressure is equal to P0 plus gamma h. This is just the depth below the surface. And so the question is, does that still hold in an accelerating fluid? Does it still vary linearly with depth? Well, apparently it doesn't, right? We know that from this expression up here. We know that the expression we had before, that, oops, don't need to do that. I know it's gone crazy here. Let's get that back. It's got some buttons on this pen that I don't want to press, but it seems to. Yeah. So we know from before that if we take this expression here, this is the expression that we use that gives us the change in pressure with depth is equal to minus rho times g. But now we have this additional term that comes into this, right? This expression here. And so usually this term here is 0, and this has just been equal to minus unit weight. And if that's the case, then we know that as we go down within a fluid, the pressure varies according to this. This is negative z, right? This is positive p. Okay, before I go on, the other thing here, this is a negative sign here, because a positive acceleration in the y direction is in this direction. This is positive. But the slope of the curve, a positive slope would be up towards your right. This would be a positive slope, and this would be a negative slope from your math, right? And so clearly, a positive acceleration in the y direction, a positive gravity as a positive constant, and this is 0, gives you a negative slope. So the sign comes in just from the math, and that's perhaps important. If you look at the fluid pressure that you go down in this, from say P0 here, we know that this expression, the rate of change of pressure with depth, is equal to rho times g plus acceleration in z, with a negative sign on it. We know exactly what that means, right? Because we've talked about it a number of times. It means that the slope of this curve is equal to change in depth and a change in pressure. And we can also write that, if we want, as equal to, we used to be able to write it as equal to, the pressure part was equal to unit weight, and this was just equal to 1, right? Just by similar triangles, right? This term here divided by 1 is unit weight divided by 1. And so in terms of what this means is that if you have a positive direction, acceleration in the z direction, this is going to make this number bigger. And so you could surmise from this that if you have a positive acceleration, if you're accelerating upwards at a z, then it's the same as you feel in an elevator. Our bodies are 90% fluid, right? In many respects, tissue is just filled with fluid. So you know that when you're accelerating in an elevator, going upwards, you feel your knees taking some extra strain because you're working against inertia. And that's exactly what this is as well. It happens to be a bucket of water, has some inertia, and it's being pushed up quickly and upwards. If the opposite, and you're coming down, then if you're accelerating downwards, then this would be an acceleration which would be negative because it's in the opposite of the z direction. Positive z is up, negative z is down. This would be positive. And therefore, if you dove down in that bottle of fluid, in the same way you feel yourself a bit lighter as the elevator disappears underneath your feet, then you would expect that gravity is diminished because this is a negative value that you're removing from. If you're unfortunate to be in an elevator and the cable gets cut, then the elevator itself will fall at gravity. And so the acceleration that you'll see will be exactly equal to gravity. And it'll be like being in this vomit comet, this NASA plane that flies over a parabola. As it goes over a parabola at the top, you're weightless for a few minutes, or a few seconds, not a few minutes, and float around inside the cabin, hope not to smash into anybody or any walls, and hopefully get brought down softly when it comes out of that into a dive. And of course, if you're unfortunate to be in a plane or accelerating downwards faster than gravity, it means you have an engine on the top pushing you down, then you'd actually have a pressure distribution within the fluid which would be negative. It would get less pressure as you get deeper and deeper in the fluid, and the fluid being pushed to the back. And so those are the mechanisms by which we can evaluate that. And so that's, I guess, talked about here. If acceleration in the z direction is positive, then you're a higher pressure gradient than if it's a static, so-called hydrostatic. So acceleration is 0 is often referred to as the hydrostatic. In water, in groundwater, because water's just sitting there. Actually, it doesn't matter if it's a water that's happens to be in a porous medium. If you go from this point to this point and it's not moving, you'll see exactly this pressure distribution, this hydrostatic pressure distribution if it's not flowing. If it's flowing upwards from a higher pressure, I guess that's a different question. And rarely do things accelerate in porous media. But this also applies not just to stuff in a swimming pool, in open fluid container, but also within porous media as well. And so that's really the essence of what we're talking about in terms of accelerating fluids. The other interesting point in this, I think, is that if you look at this distribution of fluid pressures, and we blow this up here, is if you had, for instance, a ball, I guess I don't know if I'll draw a ball. So the other thing that you can do is if you looked at the fluid pressures and how they change in the horizontal direction, then you could also look at this. So you know from this that as you go horizontally, that the pressures will change according to the acceleration in the y direction. And you can kind of see that here if you drew a line that went across here, that the fluid pressure here, as you went down from this free surface to this point, is higher than here. And so you'd expect that if you looked at the fluid pressure as you go from this point here to, say, a horizontal point here, you'd know that the fluid pressure would change as you go laterally. And this would be basically dp dy is equal to this expression here. So in other words, you can imagine what the fluid pressure is, and it's really just because you have this height of fluid that sits above you, and so long as you're not accelerating vertically, we know that if you're not accelerating vertically, then this is always going to be, then this is always going to be 0, and as you go down within the fluid, the pressure is just going to change, same as if it was a static fluid. And so the manifestation that fluid pressures would change horizontally is really a manifestation of the fact that this surface is inclined. If this happened to be enclosed, and this was open in a box to a fluid pressure, then you'd also see that along the top of this box, the pressure would change as a function of this. This is just rho A y, right? Just to finish that off. Right? So it's a manifestation of the fact that if it's free to take a new orientation of the free surface, it moves like this. If it's covered by a container lid and can't do it, then it will develop a pressure which is 0 if it leaks out here, but it will build because of the acceleration from this boundary condition. And so that's useful to be aware of. The other manifestation of that is that if you imagine that if you had a balloon in this, then one of the things that we talked about when we talked about buoyancy was the idea that you could draw a box around this balloon and you could do this calculation to look at the pressure that's acting upwards on this at this depth relative to the pressure that's acting down on it. And because of the mismatch in these, there was a net buoyant force and it would tend to rise. If you look at the distribution of pressures that you'd get along the side of this balloon, actually, let me orient that in a slightly different way. Let me take those out. Yeah, that's bad. If you draw the box around this balloon like this, then because the pressure here is less than the pressure here, then if you drew the triangular diagrams for the pressures acting on this, you'd find out that there's a bigger pressure acting on the left-hand side than there is on the right-hand side. And so there's a net force pushing it horizontally, because it's just controlled by the much more massive water around it. And if that's the case, then when this would rise, you'd find out that it actually rises on a trajectory which is orthogonal to these isobars, right? These pressure contours. So if you release a balloon from depth or a ping pong ball at depth, instead of zipping right up along this trajectory here, it'll tend to go along this. And likewise, if the balloon was tethered, it would also have an inclination that's perpendicular to that. It's kind of interesting. So all is a function of the fact that we have these different fluid pressures developed as a result of the acceleration that's in the system. All right? Thrilled by all this, I hope. If we look at, we talked about the centripetal or centrifugal pump. Oh, did I lose the guy? Maybe I lost my guy. Well, let's do this since we have it. 4, 1. Let's see if it's our crazy guy. Yeah, why not?
And welcome to So Cool Science! Science you can do right at home. I'm just hanging out on a planet in a solar-centric system and going over today's science file. And today's science file, it says, why don't the planets get pulled directly into the sun? Well, that's a wicked awesome question. Try this! You will need a mug, some ribbon, a plastic tube, and a spool. Start by getting yourself that mug and some ribbon. You're going to tie a few knots around the handle of the mug to secure it in place. Now thread the ribbon through the plastic tube and through the spool as well. Now tie a couple of knots in the ribbon to secure the spool to the ribbon. Now check this out. The mug is definitely heavier than the spool. Now, here's what you're going to do. You're going to give the spool a spin, a lot like this. Ha-ha! That's so wicked cool. Now, that's pretty wicked cool, but this is the So Cool Science Show.
Yeah, all right. That's good enough. So, a bit juvenile, of course. But the point is, of course, that by spinning this thing around, which has a relatively low mass, you can actually show that it has to be pulled inwards by the tension in this the cord. You know that because it's hanging a weight on it, which it slowly lifts up, and so it's the faster you swing it, the more the higher the other component should go as it gets pulled out. And so what's resisting the desire of the thing to be thrown out is some force that has to be applied to keep it in, so-called centripetal force. We have to make the distinction between what we talked about for static fluids accelerating and this force being present in there that changes the inclination. That's under acceleration. If you swing something at a constant velocity, of course, velocity has two components. It's direction and speed. The speed of this, the angular speed, is constant, but the fact that it's changing direction as it goes from this azimuth to this azimuth to this azimuth means that it's changing velocity, and so it's accelerating. And so it's the angular acceleration in this that is relevant to what we're talking about now in terms of rigid body rotation around a point, or around an axis, I guess. And so we could do the same things as before with accelerations in the z direction, but we'll assume in our particular case that the acceleration in z is 0. And if that's the case, then we end up with exactly the same expression as we had before for the change in pressure with depth. As you go from the free surface, the pressure increases linearly, driven by the density multiplied by gravity, the unit weight of the fluid. And the other component is that when we've talked about this before, we said that force is equal to mass times acceleration. And in our particular case, what we did was we divided through this by a volume, force per unit volume. And this term then became, as we said earlier today, is defined as a change in pressure with a direction, d r in this particular case, radially outwards. And so what our geometry is, I suppose I should define the coordinate system. We have a central axis. We're spinning something around this central vertical axis. The axis is in the z direction. If it's a container that's equal, is through the middle of your beaker, and it's being spun on this axis, then we'd expect that centripetal force pushes it out to the outside, and it would develop some inclination on what would otherwise be a flat surface, tips up towards the edges. It's symmetric about the center line. And the coordinate system is that we define a direction theta, which is the azimuth around the z-axis, a radial distance r out from it, and the vertical distance in the z direction. So those are our four coordinate directions. So one is a vertical direction, my middle finger, a radial direction, what we called y before, and now x is one that goes around it, or theta rather, is what goes, x becomes theta, which goes around it. And so these are the coordinate systems. So theta, this is really r, and this is definitely z, and that goes up through this. So these are our coordinates. So we can define pressures in terms of these. The only one that will be different from us is going to be the one in the r direction. I've derived it in the past, but I won't derive it here. We can also write this acceleration as equal to what is it? V squared over r. So this is also equal to density, which this is, of course, multiplied by the angular velocity v theta squared over r. And we can also write this angular velocity. So this is the velocity that the fluid is going around this circumference. We can also write v theta as being equal to the radius multiplied by an angular rotation, right? This is the rotation speed. And this is in radians per second. So we have to define these units. And so if we do that and we substitute, for instance, v theta into here and rearrange some things, bottom line is we end up with an expression which is this. This says that the pressure distribution as you go radially outward from the center of the axis of rotation changes as a function of the density of the fluid, which is constant. It would be different for mercury or for water. But as you get further and further out from this, then the pressure goes up, or the pressure gradient goes up. And so what we'd expect is that at any given angular acceleration, well, first of all, r equals 0. This has to be flat, right? I'm going to choose a color that will show up on here. Right in the middle here, this gradient is flat, which means if r is equal to 0, the pressure gradient has to be 0. If we go radially outward a small amount, there's no pressure change. It's flat. If we look at the pressure distribution at some radius here, which is r1, then the pressure gradient might be this. And if we go out here some radius r2, then it would double, be twice as steep. And so from that we could conjecture maybe that the surface of this should be getting steeper and steeper as you go out towards us, almost like a tornado, the water going down the plug hole. It's not the same process, but very similar to that. And so what we can do is we can ask the same two questions we asked before. One, what is the slope of the free surface that develops? And secondly, how do pressures change as you go within the fluid, either radially or vertically? Which we have. We know how it changes radially, and we know how it changes vertically, and this is merely as a function of our assumption that there's no acceleration. So let's do what we did before. We take the same idea as before. We make this d0. We get a pressure change as a function of pressure changes in the radial, the azimuthal, and in the vertical direction. Is it easier just to do this? Yeah, it is easier to do that. We multiply this one by 1. We know that this pressure difference means 0. Physically, what this means is that if you start at this point on the surface and you go round the surface, then you're at the same elevation all the way around. Of course, it has to be that way when you think about it, because if you start out at this point at azimuth 0 and you go to 340, 270, 180, 90, and then back to 0, it can't be discontinuous. It can't be going down and then all of a sudden you find yourself higher up at this point here. So by definition, you can imagine that this really is a manifestation that any curve on the surface has to be a continuous curve at the same height. It's different at this point as it is from this point, but it has to be continuous. If we make the substitutions then, so this can be 0. If we make the substitutions for this going into here, and for this going into here, and we do the same as before, on this free surface the pressure has to be 0, then we get equation 2. And equation 2 is this is 0, it's just two terms. It includes the gradient in the r direction and the gradient in the z direction, or rates of change in those. And if we just rearrange that, we end up with equation number 3. And so what that says is that the slope of this surface, and so this is the surface which is going out from this. This is our center line that we're rotating around. It says that the gradient dz dr, this, if we drew it out, would be, this is dz, this is dr. It says that when r is equal to 0, when r is equal to 0, by definition it's flat, irrespective of the fluid. As we go progressively farther out, if we go out a unit, then it has to be equal to some magnitude. If we double that, it's actually saying the same things we kind of suggested here, is that this steepens up. And so that makes it a bit more problematic for us, because now it isn't a constant. It was quite easy to calculate pressure changes with depth because it's a constant. You go double the amount down, the gradient is constant, but the pressure change doubles. And so that means that to be able to calculate the pressure at some point on here, we have to do something like integrating it. Noisy shoes. Guess it's still raining. So what we could do is you could rearrange this to get z on one side and r on the other. We do an integration. We could integrate it between z0 and z1, and r0 and r1, or we could just integrate it and get the constant. That's what we've done here. And we end up with an expression like this. And so that now allows us to say something about what the inclination of this free surface is. We know that so long as we solve it for a magnitude where we know the elevation at some point, if we know the elevation at some point, and we know what the radius of that is, then we can solve for the constant. If we want to know the elevation at a different point, we just use that constant to be able to solve it. And likewise, we can use this same expression that we talked about here in terms of this pressure distribution to calculate the pressure change at any particular location with R. So in other words, if we look at manipulating this, which is just the same expression down here, we can change that to get the pressure at any point. We can integrate both sides, and we end up with another expression. So the two important expressions, I guess, from today that come from this for fluids that are rotating are this expression here and this expression and this expression here. And they're as a standard kind of result of this. They're a bit more difficult to use than the ones that we've used before because we have to solve for a constant and we have to pin our behavior based on a case where we know the behavior. And so that makes it a bit more challenging in that regard. But the point is that we can do exactly the same things as you had before. For the linear accelerating case, we can get the inclination of this surface by the first thing we did. And we can also get how pressures change as we go either horizontally or vertically within the system. I guess the other thing that we'd know from this is that so long as our container isn't accelerating upwards at some acceleration, then the pressure distribution we'd expect to see along the edge of this is just given by our same values before, that this would be equal to dP, and this is dz, so this is unit weight, and this is 1, right? So it'll be the same. And so the pressure distribution on the side of this container is given by that. And so we can put that to use. There's one example here. It's probably shown in more detail in one of the videos, which you can go back to, but we have maybe 5 minutes just to make the case of how to use this. So of these two expressions, this is a manometer, a U-shaped manometer, U2, and what might seem surprising, but maybe not, is that if you're swinging something around your head, if you had a Viton tube which was filled with water, then the water would like to shoot out at the end, and therefore to be held in, it is in tension. And if tension is high enough to be able to pull it apart, and make a bubble, that's what we call boiling. We often think of applying temperature to do that, but if you apply tension to be able to pull it out, you can also boil it in place. And so this is a question to ask, if you spin this tube and it has water in it, how fast do you have to spin it so that the pressure at this point within the tube becomes equal to the vapor pressure of water at that temperature, and therefore it cavitates and boils in place. And so that's the basic question that's being asked. It's in English units, but let's just go quickly through it. This is the expression we just derived that gives us the pressure at a particular point as a function of a rotation speed, a radius where we are, a rotation speed, a density, a depth within the fluid, and some constant. What we could do is we could draw ourselves a coordinate system which starts off as z equals 0 at this point here, and this is equal to R, which is equal to 4 inches. We could define the boundary conditions within our system. So what we don't know is what the pressure is going to be here when it's spinning. But what we do know is that the pressure here is equal to atmospheric, which is equal to 0 at gauge, or it's equal to 14.7 psi. Even though we don't use English units, absolute. Plus. So what we could do, I think this example takes it as gauge pressure. It sets this equal to 0. It says that the pressure here has to be 0, and that's at 4 inches. So this is 4 inches. The fluid is water. We don't know what this rotation fluid speed is, and we know that this elevation of this point is equal to 12 inches. Right? 12 inches above this datum. You could choose the datum up here, and this would be minus 12, but it's easier not to. So if we know that, we can write this is equal to 0. So we can define this constant as a function of the rotation speed. And if you do that, it turns out to be this magnitude here. Now, if you know what this constant is, you could resubstitute this term here back into this expression. And now this expression is not equal to 0 anymore, but it's equal to the actual magnitude of the fluid pressure, whatever that is. And we could use that to be able to figure it out. So if you substitute this back into this expression, you rearrange this expression, including this term, you end up with this expression down here. And we want to know, we think it's going to cavitate at this point here, where Z is equal to 0, and where R is also equal to 0. And if we know that the fluid pressure that is going to be the limiting pressure is going to be the vapor pressure in gauge pressure. So you're packing up. Vapor pressure of water is 0.256 psi. In gauge pressure, it's equal to 2.56 psi minus atmospheric pressure. So this is PV in gauge. And you can solve for the one thing you don't know, which is the rotation speed. And you just need to be able to convert the rotation speed from 1 revolution per second is equal to 2 pi radians per second. This is omega, the rotation speed. This is revs per second, just by going around the circumference. I hear from the action in the audience that it's time to go, apparently. It's only just 8:50, but that's fine.